sure many of you are familiar with Agda, Idris, and Coq, and the other various independently typed languages. Well, a lot of those features that have been developed there are starting to make their way into Haskell. It's really exciting because there's a lot of opportunities to do more with the type system than we had in the past. Richard Eisenberg was the guy that leads the charge on that, so it's going to be very clear to him on how that's going. Great, thank you. Is this picking me up? That's great. Okay. So first off, thanks so much for coming out tonight on Friday night and do some Haskell presentation. What I want to do is actually sort of talk. This talk I'm going to sort of broken into two parts, and I think we'll appreciate a small break in the middle of the two parts. And so first, I want to talk a lot about dependent types in Haskell today. So, you can think about these other languages, Agda, Idris, and Coq, and these are dependent type languages. Actually, my point is Haskell is already dependent. And we're going to go through a bunch of examples of how that works. In particular, my goal for this first half of the talk is to sort of convince you that Haskell has dependent types, and dependent types are useful for doing real work. I've really tried to choose my examples so that these are things where the rubber hits road and we can actually get more work done because of dependent types. And so that's, and the only way to make that claim, right, is a bunch of examples. And so that's what we're going to see. I should also point out that my goal is not to teach everyone in an hour how to do dependent type programming. Right? So the examples, because of sort of there's 6 or 7 of them, we're going to have to be fairly quick each one. And again, the goal is to give you a sense of what's possible, and maybe some avenues to start learning. As you can see, all of the code that we're going to see is up on GitHub, so you can use this as a template to start from, do be in touch. I mean, I'm all that dependent type programming in Haskell. If you want to do that, especially if you're going to do that, do something real, like it will also be part of the product, okay, so with that introduction, that's all about the first half of the talk. Okay, so I said at the beginning that Haskell is a dependent type already. And what I mean by that is that there are 2 hallmarks that I see in dependent type. And they are that when you pattern match, you learn something interesting. There's something interesting about the types, right? So if you do a case match in Haskell, then you learn something about the types. And the answer is yes, if you're using these teachers. Generalized algebraic types, and you can see an example of that in the website. And I'm always just going to say that. That might just be something that people say, and on the rest of the world, student ratings. By the way, I realize maybe some of there's a whole. People here that know there's a whole lot of people that don't know. Just to give you an idea, so I'm right now a PhD student at University of Pennsylvania, and living in Haskell model. It's essentially what you're seeing is something else. Right, 2 hallmarks of the program. One is that matching gives you information about type. And the other is that you can have functions from types. So you can do some computation in types. And so the first example right here. This is not a rubber code, but it shows these two. It shows these 2 aspects of dependent. Okay. It shows these 2 aspects of dependent types in Haskell. And so we have the generalized algebraic data type. Just to sort of give me an idea, who here has used GATs in Haskell programming? Okay, so I say about half. Great. So this is a data type. It declares a couple of constructors. It has a different syntax than we might be used to for a normal data type. In that we explicitly give the return type of each constructor. So here, GInt is not just any GA, it's specifically a GInt. And GRule is not any GA, it's specifically a G rule. So even though these data constructors don't sort of carry any traditional information, we'll see cases where you do have that store fields. But we can actually get something useful from this. So I want to look at this match function here. So here, this is sort of an odd thing that's going on, in that we give the type GA to A. So it looks like this should work for any A. But then when I pattern match on the data constructors of G, I learn something about A. And so here, in the first line, in G int, I now know, because I have a G int, I know that A must be int. And so that's what I was referring to earlier when I said you get information about types when pattern matching on terms. And that means in the right-hand side, I can say fine, just in case anyone's very good at this. This does actually compile it. So yes, all of the examples that I show in the first episode, these are all real examples that actually do compile. You'll see I'm using PHP 783. There are a bunch of features in 7.8 that I'm using, although that has been around since the 6th. So we have that, and then the next line of match. Now, because I see that my G is actually a G rule, I know that A must be bool, and so I can produce false. And without this technique, guys, there's no way of writing a function like this that can return different types in different scenarios. So that's the first aspect of the function type programming. Pattern matching gives us information that we can use in the right-hand side of the pattern. And as it's done in Haskell, this works in both case statements and in function calls. And then the other aspect is computation type. So how many people in here have ever used a type family or an associated type? Okay, fewer. I'm not surprised. So we'll go to the next step. And so all this really does is define a function on types. So we have the type family problem, and once again, so type family is a Haskell name for this thing. And there's sort of historical good theory reasons for that. But we can just really think of this as a function on types. And so this is a function that takes types and returns types. So here, prob of int is the type car, and prob of bool is the type student. And so now in the prob function, I can take a GA and return a prob of A. And now there's all sorts of weird things going on, right? So when I know that A is int, by doing a pattern match here, we know that this G is actually a G int. So we know that A is int. Well, prob of int, you see on line 20 there, is just car, so I can return a character. And then similarly on the next line, when I learn that A must be a bool, then I can return int. And again, this type checks. And so this is computation in types. And even though, obviously this example is useful, to me, if a language can do this, then you can say that the language is dependent on the type. Because the types, at least on the right-hand side of the pattern map, really do depend on what we've done in the program. So before going any further, so this is an explanation of what I say dependent types are. A few things that sort of taking a long time to understand this. A few things that dependent types are not, I think might be. So one thing, a dependent type is not a type that depends on runtime values. Right? Sort of, I had that in my head for a while, that sometimes you have a type depending on some data that you got at runtime, right? But that doesn't make any sense. That requires time travel. Because the types are used statically at compile time. And how can we know anything about runtime at compile time? So that's not what it is. You can also think of a type as sort of depending on terms in some way, and that's maybe closer to it. But to me, still, that's not really it, because here we don't have any of that. We're not using the data kindness extension. We're not promoting anything. And yet we're still doing really interesting things in type, even in this small thing. And so that's just another thing to sort of be aware of. It's not necessarily type depending on terms. It's type information is depending on term information more than on terms directly. Another thing that it's not is dependent types are not exclusively when you have the same language for types that you do for terms.
So in Agda and Idris, you use the exact same syntactic constructs and types that you do in terms. In Haskell, you don't do this, and all of my work is not leaning toward that. But that doesn't make Haskell non-dependent type, because there's still a separation. And then the last thing is, dependent type is not a very precise term at all. And so, my definition, you could, people in the room who vehemently disagree with something I said, and then that's great, you can have the data. I don't think there's one who really can say exactly what is and what isn't dependent. So you need for choosing some of these definitions in the past today. But I don't think we can do it. Okay, so from this simple example, let's go to a real life example, something that I was actually working on this class. And that's template Haskell. So once again, so how many people in here use template Haskell? Okay, more. So let's say I want to write a function here, all names bound to X. I want to write this function that finds every name that's bound in an expression. Not every name that's used, but only those that are bound somewhere in an expression. And so I have to write this awfully large, sort of mutually recursive set of functions that do it on every different piece of template Haskell data. So those of you who haven't used template Haskell, among other things, has a representation of the Haskell language in Haskell data types. So, do that one. But one thing I can ask is for information about expressions. And so here, this data type allows us to encode, you can have variables of an expression. A data constructor is an expression. You can have literals are expressions. You can apply one expression to another. And so, again, this is to just give you a sense of what we're talking about. This is just a data type that describes Haskell expressions. But of course, an expression in a case statement, right? A case statement is going to be matches. And it's going to be much of a surprise that if you look at what's in a match, well, a match includes a pattern. Right? So there's all these different data types, and they're all mutually recursive. And so that's why I wrote a whole lot of functions to do this reversal. Now, one thing that's included in expressions is declarations. We have a let expression, and there's a bunch of declarations in a let expression. And so I want to look at this. And now, if we look down here, all of the different types of declarations, well, there's a whole lot of declarations in that solve. Only some of which make any sense inside of a let. So fundy, that's to declare a new function. So that's certainly allowed. Validate is to declare a new value. But then data that defines a new data type. And Haskell doesn't have that in a let statement. You can't have it for a local data type component. And yet this depth type in template Haskell has all of these constructors. And so it means that when I'm writing all names bound let deck, it means that I have to know an awful lot of the Haskell language to know what constructors I need to worry about here and what I definitely don't need to worry about. And so when I compile this, you may see the warning flag. It is, GHC complains, well, there's a bunch of pattern matches that I haven't done here. Right? I haven't handled the data case. Because GHC doesn't know that the data keys can't be inside of let declarations. There's no way for it to know that. Right? These are just ordinary data types. And so I get this warning, and that's bad. And so what I could do is I could have a catch-all case at the bottom and say that this is an error, but that's sometimes a set. And it also means that, let's say there's a new kind of declaration that happens in a new version of GHC, all the time. It means that I won't get any warning when I don't handle that case. And so that's or I can go and enumerate all of them and then error on each one, so that I get a warning if a new declaration is added. But maybe, for example, I don't know that I can have an infixity declaration in the middle of a line. Turns out that you can. I guess it's not everyone knows that who's using template Haskell. And so you can sort of have errors in either direction. And so Gadget can fix this problem. And so this is the proposed redesign of template Haskell. And just to sort of drive the point home, this is not an example I put together for this talk. This is actually something that might go into PhD 710. But to actually make the depth type in template Haskell, I've got it so that you can sort of have finer controlled pattern. And so this is actually taken. This is not exactly the file that is internal to PhD, but there's some edits in here. But you can see all of these different data types. You know, there's a whole bunch of different types of patterns. But the one I want to look at is declarations. And so to make this a little bit understandable, what I realized is that there's 4 different places the declarations can appear in Haskell. They can appear at the top level, they can appear inside of a class declaration, they can appear inside of an instance declaration, and they can appear inside of a lab. Those are the only 4 places that Haskell allows these declarations. Well, considering where clauses is sort of the same as left, because they emit the same set of declarations. And so I created these 4 data types, which are all just sort of rules, right? You just do that. You just sort of encode a yes or no. But to do so in a way that you have to better error. It's still working. So then I make this new data type dec context, which just tuples these 4 up, right? Because the idea is I'm going to want to be able to say for each declaration what context it can appear in. And there's no sort of ordering relationship between these. It's not that if it can appear in one place, it can definitely appear in another. Each declaration has its own pattern. So we really need to sort of track these 4 different Boolean switches separately from each declaration. And so all this dec context does is just tuple them up. So now we have all 4 of them in one. And we'll come back to these types of things again. So let's look at, say, fund. So fundy, that's a function declaration. And that can appear in any of these contexts. The only one that might be a little surprising is that you can have a function declared inside of a class because it's a default implementation of a class. Right? So in the other context, I think it's one. And so here, what it's saying is that a fundy, given the name of the function and the list of its clauses, is a dec for whether or not it's a top level thing, and whether or not it's inside of a class, and whether or not it's an instance, and whether or not it's not like. So these are just 4 type variables that can freely range over the different sort of Boolean flags that I created. So one other thing that's going on here, I'm using the data kinds extension, right? This is sort of weird. I've declared this as a data type. And so we normally think of DC as a data constructor terminal thing. And here I'm actually using it in a type. You can say this sort of looks like a term appearing in a type, but it's a bit of a lie. Because all it does is Haskell, when you say that the data kinds extension, when you say data dec context equals DC and this stuff, it actually creates 2 totally separate, unrelated things that have the same names. We get the type dec context with a data constructor DC, but we also get a kind dec context with a type constructor DC. And so we can actually see this. This is slow loading on the so I can ask for the kind of DC. And now DC here is considered to be a type with a rather interesting kind. So how many here have either seen or worked with data kinds? Okay. So here number. There's actually not terribly much deep amazing about data kinds. It just allows you to do sort of type level programming that's well timed. For a long time, you could sort of do this kind of trick, but everything just ended up to be another type constructor that you would declare. And then if you use the wrong one in the wrong context, you didn't get any sort of improvement of it. And now with data kinds, you can do this in a slightly more well-timed way. So I can't index dec by int, for example, because it has the wrong right? Int is just a time stuff, so it's normal type. Whereas if I fully apply DC, let's say this. Okay. So that's what fund D is. So fund D, it means that for any choice of whether it's top level or not, any choice of play, any choice of play, fund D is valid. And we can contrast that with data D. And here data D is, well, for any choice of whether it's top level, of course we know it is. It turns out that we get better from top level. But it definitely can't be in class, it definitely can't be in it definitely can't be in and so that's helpful. And we can look at some more obscure cases. In that can appear anywhere but in an instance declaration. You can't have a fixed declaration inside of an instance. That really wouldn't make any sense to have something related to an instance there. But actually, you can put a fixed declaration inside of a class, even though it means the exact same thing if you put it outside of the class. But Haskell lets you do this, and so I want to reflect that in counterclass. So, with all of this, let me switch over to usage. Now, if I go up to the top here and get rid of instead use my own module here. Now we don't get any warnings. Yes?
Question on the previous.
Sure.
Why did you have to give names?
That's a good question. I guess you could have mentioned right now, H doesn't have any ability to sort of type level blanks or wildcards, and so we have to do it.
Who's are getting at?
A different, yes, we're going to have underscores in types, but they would have a different meaning. Yeah, this is the question. But thank you for asking questions. I'm happy to, at any time you can raise your hand. So because of this extra information, now over here I don't get any more. In fact, if I go down here, and do that, and I try to compile, couldn't match yes and left with no anymore. And so it doesn't like scream at you, data B's do not exist unless it's pretty close. And so this again is the power of that. So now I've made my template Haskell code a little bit more type-safe, a little bit more stable when it changes. Because now if the template Haskell changes, I get warnings if I'm missing things or errors or something that's been removed from my declaration. And so that's really useful. So just sort of one other little point here to bring this home. So here, now I have to use this type of let that, which fixes the value of these indices here. So I said it's not anywhere but no let. And so because no. So here, because my all means down let takes a let back. We know that it's taking something yes and right. And so GHC can do all the matching and make sure that that's any questions on this example before we go on with it? Yes.
Does that mean something occurs in both the left and the distance?
So no, it wouldn't. So like finding could occur anyway. And that's okay because what will happen is these can be these variables can be anything. And so we'll just get chosen for it.
You got the warning.
Yes, we would. Yes, we would. If that, and if I get that one, and then we'll try to compile. So we get the warning tells us exactly what it's. Okay, so let's move on. So this is actually a module that's in base in 7.8. around, you can use this today. It's called data.type.poly. And it defines, this is actually, I haven't modified this file at all for the presentation. It defines this very particular gadget. In some sense, this is like the canonical gadget that powers them all. If we only had this one, we could do all of the others with a lot of these things. And so what it does is if I guess propositionally equal. So if A is propositionally equal to B, or the type A is propositionally equal to B, is inhabited by one constructor which forces the two type indices to be the same. And so I have two different types, but I know that they're propositionally equal because I have a piece of data, I have a term of this type around, and I pattern match on it. Then GHC will know, well, they're not two different types, they're the same. So we can do some pretty cool things down here. So let's look at cast width for a second. So in cast width, I get evidence that A and B are the same, and an A. I want to return a B. Well, of course I can. Because I just do a pattern match, I get grepl out. And when I see grepl, then I know actually A and B are the same. And so that means I can just return this. And that works just fine. And then we also have G-cast width, which is a little bit more powerful, but has worse inference properties. So that's why we have both. This one is one. In G-cast width, takes sort of a notion, proof of equality between A and B. And any computation that must assume somewhere that A equals B. And the type of that computation is R. And then we will produce that R by sort of feeding in that equality. And so essentially, when we use G-cast width, the second argument of G-cast width, you can just blindly assume that A equals B and do whatever it needs to do. And that will work. So this is using sort of higher rank types and things. And again, this is a little bit deeper. There's not going to be a grand example of this. So this shows how to use equality here. I do have an example of using equality though. And that is in this file. Okay. And so here, the idea here is that I want to have some data type that represents Haskell types. And this is not just something that, as programming language people like to do. This is actually useful. This is essentially what type rep and typable do. So maybe you see the typable constraints floating around in various programs. Well, the idea of a typable constraint is it carries one-time type information. And so maybe there's some part of your program that, whatever reason, you can't type statically. So you might carry around these typable constraints so you can learn typable. And one place that this is actually really useful is implementing Cloud Haskell. We're going to be able to send things across the network. And so we can send type information to those things. And so this example that you see here is directly inspired by practical needs in the implementation of Cloud Haskell. So here, this is sort of like a type rep. The difference between this and the real type rep is that this one is indexed by a parameter. Although, right now we're looking at ways of actually making the real type rep also indexed. So this is another gadget. And it's sort of straightforward in some way that if we get the data constructor tie int, well now we know that index is really typable, we know it's full, we can use string. But we can also do higher kind of types here, and that's just fine. So if we see that there is, if it's in a list, well, there's going to be some type contained in the list. But we know that these other type is or the other type index is a list of these type index. They're both in and with arrow works too. There's actually nothing harder about list and arrow than there are about any of the other types. Which is really interesting. That just works with that. And so here, what I want to be able to do is I want to be able to compute quality of types. And so what I mean by that is that given two of these runtime type representations, I can actually learn essentially a sort of a compile time type of quality. So because I'm handling all the cases, again, we're not actually taking data from one time. We're just considering all possible cases. And so here, in all the cases that they match, we're going to produce level. Right? I'm in the maybe monad here, for what monad is going to. And in the last case, when things don't match up, well, that's just nothing. We don't have proof that A equals B, so let's not prove. And so I just want to sort of walk through exactly what's going on in, say, just the simplest case right here. So I've taken these two tyrants, both of them have turned out to be timers. So that means we can look at our type. So this A, I've learned that, well, it really must be used. This B really must be used. And so on the right-hand side here, when I say REFL, all I'm doing is using a proof that int equals int. Of course int equals int, so that's it. If on the other hand, by the way, it does, if I change this, I do the wrong thing, and say that I want the int equals bool, well, that's not going to work. Because you can't have bool with it. Right? Because now, as I've written it right here, I know that A is int, B is bool, but REFL is only a proof that some type equals itself. Not a proof that int equals bool. So this REFL fails to affect. So I had to adopt this one. Okay, so given that, now I want to take this idea and be able to have a dynamically typed thing. So the dynamic wraps up some datum of type A along with its type. So this is something, notice that dynamic itself is not typing this. This is the essential type. And so this might be something that we can then push over a network, and at the other end, read in the type information. And then learn what type A is. You're going to type say white in that. And so, yeah. Sure. Yes. Yeah, that would. In fact, the only part of this that doesn't work with the real typable is the fact that typable is color-kinded. And to do this with the real typable, we need kind qualities, which GHC doesn't have. Although that's, like, on the train ride home tonight, I'll be working on the implementation of kind qualities, and that's happening. I guess that. But this is very close to possible. So here in Dynapply, I want to take two of these dynamically typed things. And if the types are all appropriate, I want to apply the first one to the second one. And so here I'm going to pattern match, and I want to get an arrow type out of my first dynamic. And then here, so I can match that, so I know actually that this type index A, which sort of isn't named down here, I know that has to be a function type from the type represented by TR to the type represented by TRES. Over here, this other dynamic I'm unpacking, and I'm getting it as the type TE. And I need to check, does the argument equal, does the argument type of the function equal the type of the argument? We want these things to match up. So I run this eq function, and if that returns true, again, I'm in the maybe mode. So if that succeeds, then indeed I can apply A, the payload of my first dynamic, to be the payload of my second. And I have to do all of this. If I leave this step out, I don't check that the argument has the right type. It's compilable. Could not deduce that A1 equals A2. So we could look down there and figure out those are the type of GHC assigned to the second. That's you go through names of that. And so this is really a type safe thing that I'm doing, even though it's dynamically typed, it's still fixed. Question? Yes. Yes. So I call it an existential type, and that's essentially because it has this type variable A. It doesn't appear over here. Normally, whenever we have a type variable used within in a data type. It sort of has to appear in the result. But here it does. And so it means that whenever we pattern match a dynamic, we sort of get more type information. And we don't know anything about that type, so we actually have to do pattern matching on that type to sort of narrow down the type of information. Okay. Let's see, what's next? So what I want to do now is sort of walk through and talk about this as sort of a correspondence between types and terms. And we can actually make this correspondence really tight because we use this technique called singletons. And we'll see sort of how that goes as I develop this. There's actually probably not large enough to go and for now, I'm just going to have to sort of say there is good motivation for this. We will see that motivation, but I'll say, it's sort of mutually dependent motivation in the actual technique. So we do this first, and then there is motivation for it. And so what I want to do is I want to do the simplest possible thing is encoding circle. And that is to think about natural numbers. Sorry, so natural numbers are either 0 or it's the successor of some natural. And then as we've seen, we can take data types and then use them in types. So I want to make a new data based on these. And I'm going to have all sorts of types that I have to turn on. So far, so what is this S that I created? So I'm calling it a singleton type. That's a bit of a use of terminology. It's a family of singleton types. But I'm just going to continue to call it a singleton type because it's easier. The idea, when I say singleton, what I really mean is that if you tell me that I have S at 0, then I most certainly have S0. Right? There is no other element. Okay, let's ignore undefined. There is no other element of S at 0. If I had S at of 2, then the only possible element I can have is S sub S sub S. And so this is making a very tight correspondence between this chunk of data and the type. And so when I learn exactly what chunk of data I have, I also know exactly what type. And so we can do fun things. So for example, let's say I want to be able to define addition abilities. So I'm not going to use a plus. So we're going to do it using that. And the operator here. So I want to take some singleton that. N, 1, N, and then this. Well, let's do that. And so we'll do sort of a straightforward implementation. And so this just implements addition over and over. Okay, the problem with this is that I have to write something in return time. So if I take two singleton maps and try to add them together, well, the resulting type has to be some sum of n and m at the type level. Otherwise, there's nothing I can put in that dot. Right? Here, in the 0 case, the result is going to have type s and m. But in this successor case, we need something more interesting. So now I have what it is. And so we can just write this in much the same way. now we have this as well. And this will short claim all sorts of potential. So what's going on here, the only way that you can get this last one to type check is to have our term level operation reflected in the types. And this somehow follows naturally from the fact that we're talking about these things. Right? If the term and the type are always sort of the same, then we really better make sure that we're always. And so one cool thing that you can do at this point is you can actually start doing proofs, which also include the quotes, and I'll define that about Haskell numbers and Haskell. So this might be something that those of you who program in the real type languages can do. So we can say plus is associated. And P, of course, is the letter O. And what do I want to say? Well, I want to say that if M plus N plus P is equal to N plus P. So I'll need that data kind of all. Okay, haven't gone on yet. We can actually say something like that in Haskell, which I think is pretty cool. Okay, but how can we do this? Well, we have to do a little bit of pattern matching. So let's say that M is actually 0. We do that with pattern matching with 0. Yes, that works. So I've got a warning because I'm missing these. But that's okay. So if I know that M is 0, then GHC can do a little reasoning and figure this out. So if I know M is 0, then we look at this type family definition up here. And the type family says, well, if we have 0 on the left, I can simplify. And so then this left-hand side just becomes N plus P. On the right, well, N is 0, so M plus N becomes just N. And then I'm left with N plus P. Yay! Those type checks. And in this other case, we're going to get something like that. And now here, right, if we were doing sort of, if we weren't in Haskell, if we were doing math at this point, well, let's do an inductive proof. Well, we can do that in Haskell. What do we do? That's just some recursive function. So I need to look, I need to figure out, oh, well, is plus associated for M prime and N and P? And if it is, well, then surely it's associated for N. Aha! Works! So I've proven that this type family is associated. And so, on the one hand, some of you are probably saying, well, why is that ever useful? It turns out that it is actually useful in the real program. On the other hand, I hope what you're saying, that's really cool, right? That you can do this now. So I'll admit that associativity happens to be really easy to prove in this way. Other things aren't quite as easy. These examples are curated to sort of be somewhat approachable. But you can do this with more complex problems. Yes. Sorry, just can't hear you.
If you just got rid of the KC.
Oh, so just add the recursive call. But it looks like I should be able to do that because I'm just getting REPL out and I'm producing another one. And let's see what happens when I call. We'll go to plan. And let's see. How it will be. Is it can't figure that out. And the reason is that, yeah, it comes out the wrong type, because this is a proof now that M prime and N and P are sort of have that known equality. And so we sort of need to unpack that proof and learn that. And so these REFLs, even though they're written the same, actually have they're of different types. Yes, exactly. So you do need to have them. And it's also worth noting that we actually need to have, even though there's only one constructor in our quality data, we need to actually write the constructor. Because otherwise there might be undefined or something like that. So we need to actually write it. Yes. Yes. Yeah. And so when I started doing this, we can have a proof that addition is associated. And the reason it's not a real proof is because Haskell doesn't check all of these things with other dependent languages. So, for example, instead of REFL, actually it's written undefined, and that's still going to type check. But clearly that's wrong. And so maybe that's an easy one to eliminate, so we'll clearly just don't use undefined. But the other thing you can do is accidentally just have infinite recursion. And a really simple proof like this, it's easy to avoid that. But in more complex proofs, you can end up doing that, and it would look like you have a proof if you don't. And so this is a proof that to know it's true, you have to roll it, which is a little bit. And so one thing that I want to have in the future, which is not actually my direct research, but is to actually have a termination checker in Haskell just for optimization purposes, right? Because right now, to prove that these things are associated, you actually have to run it at runtime using code. But that's really silly. Yes. So the termination checker would be necessarily anything. So the goal would be that everything that says it's terminating usually is terminating, but it will be terminating things that it will not. Right. But because the idea of using termination checker would be an optimization, it would be in that funny case, not your program doesn't run, but maybe it's not quite as efficient as it could be. Or maybe we'll have, unsafe ISert versus terminating something like that. Yes, that's right. Yeah. So and you're liquid Haskell. So there's work being done at UC San Diego, fixing all liquid Haskell. It does have information. And there are a couple of sort of impedance mismatch problems that we can't take advantage of that today. But all of this technology is growing. I'm in regular contact with that team. Bill Mercer, who also commented this actually. Okay, so that's pretty cool. We can do all of that. So let's see an application. Well, first let's see a non. So I want to have a type that stores numbers mod some integer. And so I'm doing some graphic program saying we have integers mod 5. And so I can do this using this data type and do this dynamically. The data type would store an integer and the modulus, and I can define this num, which at every step of the way checks to make sure that the moduli are the same. Right? It doesn't make any sense to add some number mod 5 to some other number mod 7. These worlds shouldn't really ever occur. So I just check that all the time. This is slow and error prone and has error elements. It works. There's nothing sort of wrong with it, except that it does dynamic check. And sort of my goal is get rid of dynamic check, do more static. And so I'm throwing this up as a reasonable idea of how to do this, but we can do this. So let's look at what I call good. And so this uses a little bit more of the singleton stuff than I actually wrote on myself. So let me pause on that. So This is the same stuff we just saw. All the same stuff that we just saw. The new stuff is down here. So first we see that I have a kind of greater than operation on these type level numbers. I'm using constraint times extension, so I can actually put that as a class constraint to assert one number greater than another. Haskell doesn't have any way of saying no. So the first thing I can say is false equals true. Right? I want some constraint that I know will satisfy. Here, in the case of second versus 0, that's always true, and so that's just the empty constraint, which is always satisfied. The other piece of this that's new here is this S-mat I. The I here is sort of implicit. And this essentially allows you to pass these singletons around implicit. In the interest of time, I'm not going to sort of go through the details of this encoding, but you can look at it later. The other piece of this that we will need is we're converting these singleton numbers to sort of real logical numbers. And this is pretty straightforward. It's not really using it. Okay, so with all of that in hand, now I've made my Z model a new type around integers. So just passing around the actual number of paragraphs, not the module. But we have an index on the Z model type that says what the modulus is. And so here, in my math class, what I'm saying over here is that we need the modulus to be greater than 0. Right? This is the absolute root. And this is also saying that we need to know what this is at runtime. But we don't need to sort of pack it up in a data type. It can just sort of float around as a class constraint or class constraint. And each time we need that little piece of information, we can pull it out by using the S-map method of the sing I class. Again, the detail, I don't want to get into the details right now, although it's not a whole lot of code. But just this idea that we can have this type index, which then sort of comes into play at runtime. And so this compilable, of course, and so I do function like 5 plus 6. I'd love to just be able to write, say, the number 4 here. Of course, this is indexed by my unary map, so that's to cover all sides and zeros. And so I can show you the function I call u, which is the unary, converts a number to unary notation. So I can do that, and it actually works. Right? So here I look at 5 plus 6 on 4 is 3. And in fact, if I try to take 5, let's say, on 7, and add that to 6, 3, let me get that. Because it doesn't make any sense to add two numbers of different numbers. So this is sort of one application of the singletons. Although it turned out you don't need the full power of singletons. And just for convenience, I also want to show one last version of this, which doesn't use that. It doesn't depend on any other of my modules. So it uses JSON built-in type lists. And you don't want to get into the details of the encoding right now, but this does the exact same. Say that. And so this, I think, is a sort of useful way of keeping track of the module of that. So you can have it in the program. Now, it makes some things quicker and faster. You don't need to pass around these modules everywhere. It's compared to that first dynamic version. And it makes things more safe. Because you get a type error right action. Okay. Let's see. Yes.
I'm just wondering, do things get slower if you use really big pods? Like, does it take a lot longer to compile or something?
With my version, I'm sure the answer would be yes. With this version, probably not. It's using non-binary. It wouldn't slow down at one time. The slowdown would definitely be. Yes.
Going back to the previous example, when you put in undefined and it's still time checked. you said that you need to run it in order to prove that you're just excluding bottom by running it.
Yep.
Do you need to do that for the entire range of, or the entire domain of the function that you're?
So it depends on the actual application. So the question was, do you have to run it sort of every number in your domain to sort of have that proof? And you need to run it every number or every triple of numbers that you care about at that moment, which in general is just one at a time, one triple at a time. And so we'll see examples of using these for the system. Other questions? Okay, so I have an example here, and I'll sort of show you. I'm looking at the clock here, and but I thought this was pretty cool and I wanted to show everyone. That you can actually define a quick check operator that just can compare functions and sees if these functions are extensionally equal. If for any arbitrary arguments, they will be the same by doing random testing. And so, when I said at the beginning, I want to walk through those examples. Here's a way you can use dependent types to actually have better quick check properties. And so here I have functions slot and slot2, and they're very similar, except in one weird case. And so I can on quick check. Equal, no, they don't. And sort of the interesting thing here is you can see that. But I can just take that. I can just sort of compare the functions directly and it does all this. So again, it's sort of leveraging the Haskell type system to let's see, so I have two more example questions. And this is sort of a big monstrous example that I'm not going to explain at all, other than the fact that it is possible. And so this is independently typed merge sort. And so if you say you have a big application that's not independently typed in Haskell, you have this one part of it which is really sensitive. You want to sort of have an extra guarantee just this one part. You can do that without affecting the rest of your code base. And so I'm going to scroll up a little bit at some point to show you that. But the bottom line down here is at the end, ignore that horrible definition of the inside, but look at the type. That's a nice type. Right? It takes integers to integers. And yet it's using an independently typed implementation of merge sort. If I had made a mistake in, it would not take it. And there it goes. So this actually comes. So what this entails, so to do that takes a fair amount of code, right? So here, instead of having, I want this to be able to be anything that could be ordered, but I need a special order constraint. And not only do I need a compare operation, but I need a whole bunch of information about this compare operation if I'm to be able to prove anything. So I need to know that if compare returns equal, that in fact the two types are equal. That's an important thing that I'm needing to prove. You need to know that if compare AB returns less than, and compare BC returns less than. You need to know that compare AC will return less than. You need to know that that is also true of greater than. Of course, that's depend on the previous time. And you need to know that if I compare AB and that gives me less than, if I switch it and hit BA, then that actually gives me greater than. And the other way around. And so it means if I want to use this, I have to sort of do all of these proofs about comparison functions. But if you step back, that makes sense. We're not going to be able to prove a sort operator is correct unless we know that sort of the fundamental comparison operation is the same. And then there's some other stuff, and some other stuff, and a lot of other stuff. So in here, I have a definition of this escort for my map1 type, where I actually have all of these proofs. The interesting thing that happens here is that I call this function plug in GHC. It turns out that GHC is a little silly. Now let's see how I have my compile this.
I'm going to get pattern matches are non-exhaustive. Because here, in this compare heap, right, I haven't taken into account the possibility that maybe the first parameter is 0 and the second parameter is sub. Right? You can see I only have 2 pattern matches and it doesn't continue. But, if I try to write that, and quite sensibly get errors in inaccessible code. In following exactly why you get that, well, this case isn't too hard. The type of compare heap asserts that comparing these types, that these types are in fact equal. Calling comparing these types returns the heap. And so, of course, if I have a suck and a 0, I'm not going to get that. And so, the premise isn't satisfying. The HCA works. What's annoying here is that if I write a line of code, I get an error. If I omit a line of code, I get a 1. And this is a bug, it's a well-known bug in HC. The ticket starts at only been 3,000. It's wrong to 9,000. No one has gotten around to fixing it. But it's becoming more critical. It's really hard to defend this type of programming. So this bug in GHC is just to squash these warnings. But I tested them on this. In the truck. I have them. Was that? Okay. Yes.
So somewhere in that file, is there like definition of sorted somewhere?
Yes.
Okay.
Yeah, sure. So we have a whole lot of stuff, and I have arbitrary instances of quick characters. So let's see some other people who can quick characters and type code. And then there's another order instance. So here is, I think what we're looking for. So I do this by using a list that's indexed by its minimum element. But because I have an empty list, I need to sort of fix an extra possibility on any type you just get top. You can't get with top on the screen at the same time. But it looks just like the main type. It just gives you one more value called top. And so here in this data, so the empty list has no minimum. Just say that its minimum is essentially positive. And then in the cons case, I want to make sure that the new value I'm putting on is less than the minimum of the list I'm and so that type is fairly simple. What becomes complicated and very challenging was two order lists, which converts a normal list into one of these order lists. And the key detail here that turned out to be remarkably hard to convince GHC of is this is essentially assuming a merge sort in that it takes this input list, splits it into two lists, and then merges them back together. That's why it's kind of merge sort. And we need to know that that splitting operation preserves them, which of course it preserves them. But it turns out that it's very hard to convince GHC of that. So I had to write this very, very proof. To do that, and it's up on the GitHub repo, you can look at it. To get this to work, I actually had to rewrite all of this in Pod and prove it there. And then transliterate that proof back into Haskell. Because it's just hard. The point of this isn't necessarily this is a great idea to do it this way now, except if you want to have this proven code in your Haskell code base today, it is possible. Again, I'm trying to sort of just show an existence here. This is possible. It's not easy or fun, but it's possible. I forgot these. Not saying it's achievement item, it's an achievement of our language scores. Questions? Yes.
So is it more likely that you would make a mistake in your proof or just in the normal implementation of merge sort?
The proof is checked. And so the way I could make a mistake in my proof is if I accidentally had an infinite proof. That would be sort of the only easy way to do it, or unless like I accidentally type on the phone. And it actually turns out pretty easy to avoid infinite recursions. Everything is nice and structural. And so you could do a fairly, I can imagine writing a template Haskell program, for example. It would just check for structural recursion. And then I have pretty good confidence. Other questions? Oh, yeah, sure.
So it seems like when you're doing all this stuff, you're basically seems like runtime computation is easy, type-level computation is easy. The real hard part is correspondence. That true. I feel that it's true. Because, like, for example, like, that's what you sort of right? You can probably define, you can probably write, you create a program which describes that type of computation, highlight how, and then a part which is like, there's a right all type of stuff. Right. And then the hard part then is, and you sort of confirm this, the real hard part is the correspondence, right? So, like, how, and I don't know how, like, the tools are, how.
So there's a couple different things. I don't actually think it's the correspondence between the types. The correspondence is sort of captured in that snap. The problem is that you need, any algorithm that you write is going to have to respect certain invariants. And so you need to sort of have proof that it respects those invariants. And so in the case of split, the type of split name sort of is the one that's hard to ascertain. That if you take some list and split it, that the minimum of the split list is going to be the minimum of the original list.
Okay, so
but that would have to happen if you did this in another dependent type running, would you have that same verb?
right. I mean, I'm not saying that. I'm saying that is the burden, right? The burdens of the seams like that, like split.
The hard part is always moving in your program is correct.
It's not exactly. It's not writing the program in the values or the type of. It's always the correspondence.
You could say I wouldn't call it the correspondence.
Yeah.
But yes, and I think if the programs themselves are simple, it's proving that it's correct and producing the type of. So yeah, maybe you're right. You could say it's making sure that you're maintaining these correspondences.
Yeah. So I guess actually, that is how in your experience, have you found you suspect that there's
The world of dependency type programming is still sort of young in some respects. So, in fact, at a conference earlier this year, there was a published paper which, in my opinion, sort of the paper was just, I wrote a dependency type programmer, and it works. And this is like new and exciting and publishable. And not only that, I wasn't making some of this. But what was interesting here is that there's a couple of techniques in that paper that make it generalizable and ways of doing this better. My hope is in 20 years, we'll all know more about this, and it won't be so bad because things will just be set up. I have thought a lot about how all this sort of fits together. I haven't thought much about writing beautiful dependent type code. I am sure there's a much better way to write a dependent type code. But you have to ask him about this. Okay, so let me sort of wrap up this section with one last thing. This is going to be very short. And that is, again, more type level computations are helping us. So this is a case of doing dimensional analysis, Haskell, and how, again, I don't want to get into any details, but even though I put in information in different units, because the types of tracking everything, I don't have to worry about unit conversion here, because it's all encoded in types. And so, sure enough, if I ask for a one from here at home, will be in minutes. And this is auto converting. So notice that the length I've given is in kilometers, the speed I've given is in miles per hour, and I'm asking for minutes. And there's no, we don't see any sort of conversion going on. And in fact, if I ask for my journey home, you see that's the time, right? If I ask for that in miles, well, you can't have time. So this is showing, again, how a lot of my mind code is simple. Pound is an operator. So actually, like a mile is it's it's both. So that's why that is. Okay, so with that, let's take a 10-minute break, I think. And then this is the second part is sort of the first. And then we'll resume at 5. Okay. So this is going to be a little more theory and more stuff. And this is all about where things are going from here. And so, as I say right here, this is all preliminary. None of this is set in stone. And I'm always worried about getting nasty emails from people saying, stop doing this to ny-haskell. And so far I haven't gotten to this. But this is sort of an opportunity to try to get a wide audience for these ideas, so I do get feedback. And so, I'm developing a little bit. Sure. Okay, so to repeat the question, why do we care? Why, if we have these kinds of type 1s, why do we need another one? Why do we do this? And there's a couple of things about it. The first is, it seems Haskell is wanted. Because people have been trying to squeeze in type of ideas into Haskell code for a long time. Basically, ever since functional dependencies. This sort of idea, people try things in some ways. And so maybe you could have it for real instead of problem. Another is Haskell is a little bit more mature than the other one. There's a whole set of libraries that we can work with. And Haskell has what I think is sort of great compiler. The reason I say great is because of its optimizations. Haskell can produce really fast code. And the other ones don't necessarily have that. Although you can extract from Haskell and then it's really hard. And I think, for me, sort of from the academic side, the other interesting thing is that Haskell has this long history of really strong type resists. None of the other languages do, because no one's really figured that problem out. And that problem is how can we do independent typing while still preserving all the typing group properties that Haskell is dependent on, and all existing Haskell programs still have. And so those are some of the answers, but also it's fun. I mean, on a very personal level, that's why I think. But I think that people will find success.
So an example of a sociotaking condition, you could use sort of shift case that like particles occur, like doing like case groups to
Yes, so that's part of Haskell magic, is that I didn't have to say exactly what reflexivity I wanted to use or exactly what reflexivity I got out. It just finds the right one. And actually, in some ways, it Haskell proof in the merge with the simpler compiler, because the compiler is very specific about if I was using commutativity, I had exactly where I wanted to use it, whereas Haskell said, I just want to use commutativity here, and the case would figure out what I want. So, in some ways, it's a little easier to use, although currently most of it's not.
curiosity.
Which one? Type check. I think Haskell by the way.
You not get the inferences.
Yeah. But you know what? That was not accurate. Because I was doing a sort of Emacs integration of talking, so it's not Haskell. So maybe not. Okay, let me talk over. So let's just jump back into these.
So, in the interest of time, I'm not going to go into a whole lot of depth about what all this does. But the interesting things, we haven't seen those. This is using sort of a built-in single-move library, which generates a lot of this stuff for us. And what this is really about, this example, and this is scope of the files, is we have a length index vector. So we have this vec type for the top of the screen that keeps track statically of the same. And we have this replicate function, which can take a value and repeat it so many times, depending on what I'm doing. And so that's all well and good. And then down here, what I want to have is I want to have a list of vectors, perhaps of different lengths, and I want to be able to concatenate them. And so, of course, if I have a list of vectors of different lengths, to have this be well typed, I need to keep track of all the different lengths. So this list, I'm going to use this type F list. And the idea is that I'm storing a type level list of the length of all the different elements in the list. Again, looking at the high levels, not the detail. But I can build one of these things. I have to have append on vectors, and of course, if I append two vectors, then the result, the length of the result has to be the sum of those lengths. And then when I do concatenate, I'm going to want to compute the sum, which is just folding the plus sign. And so we can do this today using some power from the single compilable to promote functions to type things. And so there's this promote thing that you see on line 34. That's just some template Haskell stuff. It goes over the code that I've written there and promotes all the type. And so there's a library called singleton that's not happy with those all those. But that's somehow unhappy to have these things. So this is what I want that code to do. And of course, if I try to compile that, of course, it's interesting. But someday, we're not going to have it. And the vec type is mostly the same as the last one. Except this one's actually indexed by real integers instead of this funny math type because it's not. Here we see right here, as well as this thing down here, we can just take term level things and promote them to the type level with a tick mark. Much like right now, those of you who figure out the data kind, you can take data constructors and promote them to the type level with a tick mark. I'm just extending that. Yes?
I thought we wanted the vecs to be indexed by nat so that they wouldn't be negatively sized.
Sure, we can have that if we want.
Okay.
But I chose to do it by integer here. Okay. Maybe that's fine for everyone. So then, the other interesting thing is now you have this new type of replicate. So let me bring up the other file. And so what this is a new thing instead of for all. So it's syntactically just like for all, but it's the pi bound. And something that's pi bound is available both in types and in terms. And that's sort of understanding that sentence is what the rest of Polygon, just as I'm packing up one, is you can now write something in type and in time. And so what I mean here is that this n is in types because I can mention it later in the type. That's what the return type uses n. But it's also in terms because I can pattern that on it down to. So the other funny thing that you see here is this at sign that I'm using. And that's because normally one of these pi-bound things would be inferred. But I actually want to make it explicit here. So the new bit of syntax will be to use an at sign to overrides the implicit nature of that. And so this is what I want the replicate of the future to do. And without all of this things, this is considerably simple. No template Haskell, no extra library we need. Okay, so let's jump back to the keynote. Right away, I do want to say, right, as I'm thinking about extending Haskell, all your old Haskell programs will still work.
except for things that use let to generalize over times. Right? There's a paper entitled Let Should Not Be Generalized, and actually a few years ago, JC became a little bit finicky about let generalization. No one noticed because no one notices. And now I'm going to do the same trick at the time level, and again, no one knows. But a key fact here is that termination is not going to be required. And so people who think about dependent type say, oh, well, does that make your language inconsistent, and then we can prove false and things. Sure we can. We can prove false in that. So that's no problem in Haskell. We have undefined. We have general recursion. We're okay with it. And so you won't be writing proofs in Haskell in a mathematical sense. You'll still be able to do dependent type programming. And maybe GHC might move every now and then. But better GHC move sometimes. And then when it actually succeeds, you know your program moves. So that's okay, so I'm going to talk about this a little bit and then say actually what's happening. So this change is all about the quantifiers. So a quantifier is something that introduces a function. And right now, Haskell has 3 different quantifiers. It has for all, which introduces sort of a type level function argument. We have arrow, one of those used to, and double arrow, which introduces it's a sort of term level argument, but it's invisible. We don't actually have to. And looking at these, we can ask 4 different questions about quantifiers and the quantifiees of the quantifier. So is the quantifiee relevant? Is it dependent? Is it visible? And is the quantification required at all? And so the next 4 slides will define these. The quantifiee is relevant if it can be used in a relevant context. So that's sort of the accurate definition there. But with an example, I think maybe this brings it into some level of clarity. So for all is an irrelevant quantifier. The 2 arrows are relevant. So the first order, you can think of this as around at runtime. So it doesn't quite tell levels. So in this case, V is for all quantifier. But this first two doesn't make any sense. I can't then take not V. Right? That's wrong. You can't then use V in a term. And that's because V is a compile time thing only. And we can't then return it at runtime. That would make it relevant. We don't want to do that. But this is okay. We can still mention V as long as it's to the right of the double call. Right, so this is using scope type variable. Whereas with arrows, we can always use an arrow down argument later. The reason I say it's not exactly the same thing as erasability is because we want this idea of relevance also in type families. And because all types are erasable, then it doesn't make sense to talk about erasability in types. So it's just slightly different than erasability because I want to do. But in terms it's the same. So there's dependence. So this is whether or not the quantifiee can be used later in a type. So for all is dependent, and the others are non-dependent. So here, foo, that makes good sense, right? I can use A later in the type. And down here with bar, well, you can't do that. I mean, even when I see that, I have a hard time even parsing what that means exactly, right? So these are jumping. We just know we can't use. We can't use the later type. The next question we can ask is visibility. And all visibility is do we need to actually write the thing in our source code? So arrow is visible. We need to write arrow arguments in our source code. But we can leave type arguments out and we can leave dictionaries. And so the example here is in foo, when I call foo or I define foo, there's nothing to the left of my equals sign. I'll just say foo because both the for all bound V argument and then the same I dictionary, those are both implicit or invisible. Whereas in bar, I have a visible parameter of the same thing. I actually have to mention call C and define it. So we have this reasonable, visible, and invisible. I often think of this as implicit versus explicit, but evidently there's people that have different meanings attached to those words, and so it makes it clear to use visible and invisible. And then the last is requirement. If we want an arrow-bound identifier, we need to actually mention that in type. We don't need to write the word for all in type, that's just preferred using the three variables. So yeah, don't write the word for all, but that's all required. So let's sum all of this up. So for all is irrelevant, is dependent, is invisible, we don't have to put type arguments in to infer the unification, and is not required to be inferred using the variables. And you can see through the arrows we have different distinctions. So under visible, when we have a double arrow argument, that's inferred by solving. Right? You sort of look around for instances, which is a different algorithm of unification. So that's one distinction. In Ruth's program, Agda, the difference is the single braces versus the double braces. Does anyone know what I'm referring to? Awesome. Okay. I'm going to expand this list. And so the big new thing in this is that now we have pi. And it turns out that sometimes we're going to want pi to be visible and sometimes invisible. And so we're also going to have modification that in the for all syntax, you have for all and a bunch of things and then a dot. But we're going to generalize that and you can have a dot there or an arrow. Arrow means visible, dot means invisible. So this is a conservative extension of what we have today. But the interesting thing here is that the two pi rows are both relevant and dependent. So that means you can use it later in the type and you can use it in the term. And we'll see sort of another example on the slide. That's the new interesting thing about it. For completeness, it also seems to make sense to have for all arrow. It's unclear whether or not anyone will ever use it. Right? When we call the id function, we will have to pass in the type. Maybe, so people want that to happen. But for all arrow, that's just syntax. So let's see the example. This is a slightly reformulated version of replicate, and I think is a little bit more perspicuous than the one we saw earlier. So this is the same exact type that we saw in today's example. And here in replicate, I'm going to use for all to bind the A, because I don't want to have to worry about what my element type is in my vector. I don't want to have to pass that in explicitly. I just want it to be inferred for the unification. But my pi bound identifier, I'm using the arrow here. And my syntax highlighted in my slide is intentional. This arrow is not really the function arrow. It's a piece of special syntax related to pi. It just happens to be spelled the same as the real function arrow. This one versus green. Right, so green meaning type, blue is keywords, and white is. So here, I'm pattern matching on my value for n. And that's the 0 and sub. Down in function definitions. But I'm also using n. So this pi bound identifier is exactly the same thing as using singletons. Pi n is the same as for all n sing. But now it's built in and actually can be much more efficient. Because singletons require sort of conversions back and forth in singletons to regular types. So that's really all that we're doing. It's just adding pipeline types. And that's really all we need. Turns out the implementations a little harder than that, but that's what's yes. No, you can find this. So the question is, can you quantify sort of over anything? The answer is yes. There's nothing special about maths. Yeah, sure. So if you don't know that number at compile time, you can read that in from the user runtime and then call replicate. And it just means that at
during compilation, we're just going to have some unknown variable n, which is the length. But as long as it's sort of the same everywhere, it obeys all of the rules that we set out in our different types. So we have a choice. The way I've written here with the arrow is the color of these would have to pass it in, even though it can be inferred. So it's sort of redundant. But in some cases, it only can be inferred by the return type. And so maybe by making it explicit, now we avoid some type issues. And so it's a designer's choice. I could replace that arrow with a dot. And then it would be okay, so there's a couple other sort of knock-on effects to this. Right now, Haskell has a separate type system from its kind system. And I want to go away with that and make types and kinds the same. So that means that everything we do in types, we can do in kinds. So that means the type system to work in kinds is something I personally really don't have kinds in. We can have kind families, because types are the same. We can even promote gaps. Right now, so I've used some sort of data types at the kind level. Well, there's limits to that, and I want to get rid of all of them. It turns out this piece I've already implemented, and it works on my work. So that's how so we have it. And another effect of this is that now, if we want, we can have kind variables explicit. So here I have a polykind data type T, and today I have to read up the K, but here what I've done right is I have this kind K, and then B is a kind K, and then GHC can infer that A actually has to be a kind K or a star, and this all works. I gotta get my branch, I'm going to say that. It will not apply. It says for all. It's wrong. Yes. Oh, no, you do. Absolutely. Yeah, because that will know that n is math. So if I wanted to leave off that application, absolutely. Just say pi. Oh yeah, you can do it in order. I could come first if I wanted to. But I'm not sure. You can maybe ask me after this. I'm just concerned about the time. So for all the detail there, there's a paper I see a few left here that outlines exactly how it's going to work. And it turns out the implementation really matches the paper, which is really important. This is implemented and okay, there's still a bunch of other questions about all of this. So, what do we do about, if we want to promote something that has a constraint? Do we promote dictionaries? I can do that. Right now, type families have to be saturated. What we're going to do with that termination where we talked a little bit about the other sources of the topic checking. The good news about all of the unanswered questions is that we can handle them one at a time. And so we can have this whole thing working, and even if we haven't addressed any of these, we'll see a lot of useful stuff we can do. We can choose which question we want to hit next. Do that. And then each one looks like a conservative thing. So I think it's okay to do one. So let me tell you what is happening. So some of you can see the core language. The GHC has a typed core language. That is mostly done. All of the stuff for the universal promotion, that's all done in the core language. That was done a year and a half ago, actually. And outside is still working through. So right now in that branch where we try to compile the file, that's one definition of the policy. Type inference, I worked out an algorithm on paper. I have partial proof that it's correct. There's nothing stuck about it, but I just ran out of time, picked it on path, and I went back to it. This is all sort of roughly in progress. And so that's coming along just fine. The implementation is coming along just fine, and like I said, I'm turning along really well. The interesting thing here is, I want to keep typing for some nice theoretical properties of typing, which is something that's only different. So the next steps, I want to merge the type equals kind stuff into the master. It turns out, sort of referred earlier, so that we want to be able to do these sorts of qualities in Cloud Haskell. The Cloud Haskell thing might be pushing me to sort of merge this even sooner, which is great, because I have found out to engage in probably a long and vigorous debate with Simon about all this stuff. He's quite aware of everything that's going on, and it's just sort of being slowly dragged along, not quite getting into anyway, so that's going to happen, hopefully for 712, that will not 7. And then all the Pi stuff, that more likely 714, and maybe by that time and then some weird parsing issues. And then we'll have to take cuts, and we're done. Probably at the same time I will graduate. As I said, this is essentially music. And that's it, and we have, I guess, 6.5 minutes for questions. No, I have contacts or something that well to know. My efforts have been more for implementing it, and then hoping that the use cases come up as a result.
To repeat what I said last time we talked, thanks for doing this wonderful work.
Oh, well.
And so I know a lot of people want us to deal with not just deal with different things that they find challenging when they're trying to figure out how to do these encodings in current modern Haskell. Where have you been sort of surprised with what people find more manageable or more challenging in leveraging the traces you can?
Good question. Where do people sort of run into trouble with what we have?
It's a singleton construction that usually makes something first, I think.
Well, yeah, no, I haven't had too many people sort of singleton usually work out okay. Closed type families for people who lose a lot of times because in corner cases are very, very serious. I don't know if I have an answer to that. There's no pattern to that. We've got time for one more quick question. So pi is originally taken from sort of the use of capital letter pi to denote a product. The way that capital sigma would be used to express a sum in mathematician, and it's called a dependent product, and that's just I think that's it, guys. If you want to talk to Richard more about this, you should swing by the bar with us. We're going to Jake's Saloon over on 23rd Street between 7 to 8. All right. Anyway, the entire group or many people will be going there, so you can hit them up with your questions then. Great. Thanks so much.